quote, resolve the singularities, so in quotes, just because we're not literally going to do that in the conventional sense, of some algebraic variety over K, we first fiber it by curves, right? So this is what we've learned in the previous discussions. And so precisely what that means is we find some modification of X, but let's say the variety is X, sorry. Should actually give it a name. All right, so we find some modification, let's give that a name even, say X prime to X, where a modification is a fancy way to say, right, a proper birational morphism, right, proper birational.
No, not birational.
Well, at first, yes. At first, yes. Like
sorry, modification alteration. Sorry, I got confused. Sorry.
Yeah, that's okay. That's okay. Yeah, later, yeah. In the next step, I'm going to take an alteration, but for now, like at first, to fiber by curves, you can just take a modification usually. I should be a little careful, I guess. Like, you know, if your field doesn't start off algebraically closed, then you might have to take an alteration just to make to make a finite extension to get some points. Like if you don't already have, you know, some points over your original field, you might have to take some extension. So I'll just write that sort of in parentheses just in case. Right? So perhaps an alteration if you start with K not equal to K bar. Right. So if the field isn't already algebraically closed, you might have to take a finite extension. And then if you base change by that, that's some alteration. But if you allow yourself to start with K equal to K bar, the modification is totally fine. Yeah, okay. Okay, so in an effort to resolve the singularities and variety, we first fiber it by curves. So we find some modification with certain properties. So such that, sorry, I should do this actually. And zoom in a bit. Yeah. So such that there is a morphism, right, which goes from X prime down to a projective space of dimension 1 less than X. D is the dimension of X. So that X prime is a projective variety. You can start off with any variety, actually. I didn't start off with a projective variety. I started off with just any variety. And then you can actually make a projective, use like something called Chow's lemma. And so you can have this be a projective variety. You can make it normal, even by normalizing. So you kind of immediately put yourself back into the classical setting by doing some sort of modifications of the variety initially. So it's a projective normal variety. All of the fibers of F are curves. They're all dimension 1, I should say. They might break up into pieces, so they might not be irreducible, but they're at least dimension 1. But the generic fiber is smooth. It's projective just because the variety is already projective of genus G. What else can you say? Yeah, so smooth projective of genus G. And we can even make it so that the smooth locus of F is dense in each of the fibers. And that actually is important because it allows us to conclude that the fibers are connected by some argument about Stein factorization or something, but let's not worry about it. So basically, like, you do some modification at the beginning, maybe an alteration if you didn't start with an algebraically closed field, but that's kind of minor. And then at the end of the day, you can say that, quote, after a modification, you just compose all of the ones that you need to take. X is fibered by curves. Right, that's the idea. So it's a family of curves.
Well, what's the geometric reason they're connected?
So you take this thing called the Stein factorization, which so I want to I'll draw a cartoon in some sense, which actually I kind of learned from you. I don't know if you remember, this was a while ago. Like, the Stein factorization is this thing that you can do with any morphism, actually, where you take the fibers. So I'll draw some cartoon, but of course it's just a cartoon, but it kind of gives the impression.
That'll be an alteration, right?
So here, let me explain. So the Stein factorization of F, actually. So what I'm going to do is form some intermediate variety between these. And the way that this intermediate variety is constructed is by taking the fibers of F, which might be some curves or something that look like this. This is not a good picture. Here, let me zoom in. All right, so you take some fibers, which, so it might not be connected. There might be some connected components, and then you crush them, or you do contraction. So this one maybe goes, over here.
Okay, take components. Okay, but
yeah.
But that's not a modification. Oh, you use Z instead of PD minus 1, I mean?
Yeah, you could take Z. Yeah, you could take Z. But
Instead
then
of PD minus 1.
Yeah, but then the miracle is that then this would be actually a tall and finite.
Not on the whole space. Why is it on the whole space?
Yes, so it is on the whole space because of this smooth locus being dense in each fiber.
Oh.
So
Smooth
yes,
locus being dense in each fiber.
what's that?
Yeah, how did you get that to happen?
So that happens by the construction of the family, right? Like we know that the way that we get the family is by taking some intersections with linear subspaces.
Okay.
Right? Yeah, and so it turns out that we can arrange that the intersections are such that generically the intersection is smooth for each of the curves that we get by cutting. Is that all right?
Yeah.
Yeah. So the smooth locus turns out to be dense, and this is not dependent at all on the characteristic. This works regardless of the characteristic, right? That's something that came up in a previous talk, right? That maybe the first one, and that was a good point. If you inspect the way that this is constructed very carefully, you realize that it's really about intersections with appropriate dimensional linear subspaces, and this has nothing to do with the characteristic, actually. So you can do this without worry about this. So the point though, like the point of this bringing up the Stein factorization is not just to bring up some sort of fancy theorem. It's that you see, like once you, well, sorry, I have to get rid of this. What's this? Get out of here. Damn it. Come on. No.
Yeah, I don't know how to get rid of this. Sometimes this happens and I cannot get rid of this.
Oh, this is annoying. This is
Yeah.
This is terrible.
I'm getting tired of the internet next.
But this is not internet. This is
Hey, drag the windows that want you enlarge the middle and you drag to the right side. That should be get rid of this one.
What's
You
this?
see the wait.
I've tried to drag it to the right hand.
No, to drag the nodes, enlarge the nodes.
Enlarge the node.
Yeah, you see the middle there. There's somehow like a. No, not this one.
Oh my god.
Hey, enlarge what?
The nodes, the note taking app you are using.
yeah. That's
Oh,
correct.
there we go. Great. so the point is that so for everyone is interested in this, you make the smooth locus dense in each fiber, and that's what makes the morphism that I get here from Z down étal, actually. So let me. This is the chain of logic, is that the smooth locus is dense in each fiber.
Oh, but
That tells me the fibers are connected well, tells me that this is étal, actually everywhere. Then this is an étal cover of the projective space, right?
yeah, there are no such things.
Exactly. So Z is already PD -1. Yeah. Is this good? Makes sense?
Well,
Okay. All right. So yeah, so that's one of the reasons you want to know this immediately. Yeah. So I'm happy to take any other questions about this, but I do kind of want to move on from this step because I have to get somehow to the 3-point thing. Right, so I don't want to spend too much time on it. So.
okay, please, yeah.
All right, so cool. So after some modification, X is fibered by curves. Now, once you have a family of curves, you say, well, maybe we can make the family kind of nice, right? So the sort of heuristic is, can we make the family sort of better? And by better, we mean, can we make the fibers have, at worst, nodal singularities? So currently, I mean, the singularities in the fibers could be terrible, right? You could have cuspidal singularities. And so the picture that I kind of have drawn in the past is, right, you have this, you can imagine a surface or something. It's not literally a surface. I mean, your variety could be any dimension, but suppose that you have some surface and the fibers then kind of look like this. And then there might be some degenerations. Things like this could happen along the way, and you could even have cusps. And those could even have a cusp like this and things like that. And what you want to try to do is make the family better in the sense that you get rid of these cuspidal singularities somehow. But the sort of slogan or the statement is that you can't really do this unless you allow yourself to make some base change by an alteration, which is a finite cover in general. So I'll just say that quickly in words. So after some sort of finite base change, some sort of cover of the base, not literally, but kind of, we can improve the family of curves to have fibers with at worst nodal singularities. And so this is a pretty cool argument, right? Because what you do is you say, you know, away from some closed set over which the fibers sort of degenerate, so away from, say, some bad points, there's an entire open dense locus of points over which the fibers are smooth of genus G and all of this. And so what that means is that we get a map. Right? This is all kind of brief, just because I don't want to spend too much time on this, but we have a map, a morphism, right, from some open dense locus in the base, say, let me not call it PD -1, just because it turns out that we might want to call it Y, actually, in general. We might have to sort of change our base a bit. So let's just call it abstractly Y. So some open dense locus, and that has a morphism into a moduli stack, which parametrizes the objects that we have in the family. And the reason why I'm not being terribly specific about what that moduli stack is because we might, depending on how we make the family, we can kind of change that stack. Like, it depends on what type of objects we end up with. In particular, you could have the moduli stack of curves of genus G. You could also choose to make it the moduli stack of curves of genus G with some marked points. So let me write this. And I'll kind of explain maybe quickly in words why you get to choose this. So the genus G thing is going to be sort of consistent, but you could either choose to have the marked points or not. Sorry, and marked points, right? And actually, what I'm learning recently is that, and yeah, I'm not exactly prepared to talk about this in great specificity or detail, but what I'm learning now is that you could even take this to be some more exotic stack, which is called the Kontsevich space, or the Kontsevich moduli stack of curves, which actually is kind of relevant to what I'm going to say next. I'll explain why, hopefully, in a bit. So this is actually not the stack of curves, but rather the stack of maps of curves into the space in some sense. And maybe I won't get into that too much, but I'll just say, like, that's another option that you have in some sense. So, you know, yeah, so how should I say this now? So, yeah, so you have this choice, and a priori, like, the family we have is a family of curves of genus G, generically, and I haven't marked any points or anything. So I guess I could kind of try to proceed with the argument without marking the points and see what happens. And you know, like, you say, well, wait, you have to be careful because, like, maybe the genus isn't big enough or something like this. You say, well, no, it's fine. You can actually make the genus as large as you want. And that's, like, an important thing to maybe mention, is that, you know, at the beginning of this whole argument, we could have twisted X by some Veronese embedding, which just means, like, take the monomials of degree D for an arbitrarily large D, right? Just kind of, like, make it really big, right? So let me say that. So at the beginning of the argument, twist X by a Veronese embedding of arbitrarily large degree. To make the fibers have arbitrarily large genus. So you can make the genus actually as large as you like. In particular, you can make the genus greater than or equal to 2, right? And the reason why you might want to do that is then you could guarantee that the moduli stack mg for g greater than or equal to 2 is what's called Deligne-Mumford, which means it's like a pretty nice stack, like you actually kind of know some stuff about it. So we could have also done this by marking points, but maybe you don't want to do the marked points argument because it incurs some alteration or something like this. Anyway, so you could make that happen. And then once you know that, there are a lot of results that go into this, but you can actually guarantee that there exists a scheme. Let's call that thing, I'll just call it S over mg. Well, let me just actually just say what it is. And it's this thing called the moduli scheme now of curves of genus G with n marked points. I could take n to be 0, right? N could be 0. So that's totally fair. And level L structure. Level L structure just means you pick some sort of isomorphism of the Étale cohomology of the curves in the fiber. So I don't know, I guess I'll call this like X sub Y with Z mod L coefficients, right? So you pick some sort of isomorphism, that's the level L structure. And then you have to say what L is. Well, L can't be divisible by the characteristic, and it has to be, in general, I think it has to be bigger than 3 or something like this, or it could be 3, depending on what's going on. The point is that there's some scheme though, and a finite Étale morphism, which goes from this scheme onto the stack. Remember, always G is greater than or equal to 2, and what I'm saying here, or else this is like not really true. Right, so there's some finite Étale morphism which is representable by schemes. And so what does that mean? That just means pullbacks along morphisms from schemes give schemes. And so the way that you apply that is you just say, well, I have this map or this morphism, right, from some open set, which is the scheme. And I have this scheme living up here. And this is a representable morphism. Well, representable by schemes. Right? And it's finite, which means that it has, like in some sense, finite fibers and Étale. And then I can pull back along this thing again, this is sort of a review from the previous discussions, but it's kind of relevant to say all of this, right? And then you could project onto U, and then there's some argument about, right, using this, the geometry of this moduli space to improve the family. So I'll kind of go through that very quickly. So use the geometry of this moduli space to improve the family.
Is this an alteration now?
Yeah, exactly. Yeah. So I'm going to use an alteration to do this.
No, you have it. This is already is an alteration over U.
This thing here, you mean?
Yeah.
Yeah. This could be, yeah. Let's just say that it is. Yeah. The problem is that this might break up into irreducible components, and I don't want that. So I'm going to pick some component, and then I'll work from there, and then it's an alteration on that component.
Okay.
You know? Yeah, but yeah, that's exactly.
This is where you're giving up the modification.
Exactly. This is exactly where I did this up. Yep. And in some sense, this is where you have to give it up. Like all the other alterations that occur in the argument, I think are sort of they're not really essential, but this one is absolutely essential. It seems. I don't see how to get around this, and it doesn't seem we know how to do
But
that.
this idea of making the genus very large and using genericity.
Like so that the map is sort of generic.
So that all the Riemann surfaces are ugly, so they don't have any symmetries.
Yeah, so I'm going to try to explain why that's not enough. Yeah.
Okay.
So you see what I've done so far is I'm hinting at this objection to needing the points.
Yeah.
Right, because I've started off with a large genus. I'm saying at the beginning you can make the genus as big as you like, right?
Yeah.
I'm going to show how this argument sort of breaks down if we don't have the 3 points. That's what I'm going to try to show. So we have this map, and then we pull back, and we get this new family. Well, this new sort of thing over U, and so let me quickly do the argument that produces the alteration.
Can I just before you go on, the fact that the right hand side map is a étale, that does imply that that scheme on top is smooth, right? Non-singular. I mean, I know its closure has singularity, but I think
it's okay, because actually everything I've done, I've not taken the closure of anything yet.
No, but my question is, does this, because I don't know what happens on the stacks. I thought a stack is something smooth, and then an étale over a smooth should be smooth. So is that, am I right, or is that not right here?
Oh, an étale over a smooth thing should be smooth. Yeah, no, I think you're correct. Yeah.
Oh, okay.
Yeah, I think this is correct. Like, I think this is smooth. Yeah. Yeah, like in the sense of stacks, this is smooth. Well, this is a scheme now, even so we don't have to worry about this. This is a scheme. It lives over something that's smooth or regular or whatever, and this is an étale morphism. So yeah, this should be a smooth scheme. Yeah. So at this stage, this is a smooth scheme. But once I start taking the closures of things, I'm going to ruin that.
Right. That's the problem. Yeah. Right.
So I'm going to ruin it when I take a closure. But at the so of course all of this is at the expense of an alteration. What I'm going to do. So let me get to that step quickly. So yeah. So let me write. This breaks up into pieces. It breaks up into pieces. Think about, like, if you fiber something, you might factor it into pieces in some sense. Right, so it breaks up into some irreducible components. Pick one of them, let's say U prime, and that maps in by some closed immersion or something, or some closed. It's a closed set, and then you can call that map into that thing, call that G. So some inclusion, right? And then we have this inclusion by G into this fiber product. And then that thing lives in the closure. Sorry. this thing lives in the, we're using a lot of facts, right? I mean, that this thing even has a closure, of course, is like a theorem, but you know, whatever, there's a closure. And it turns out to be, you know, why? Because U is dense in the base. So when you close it, you actually get the whole base again, right? Closed, everything is closed now. So this is closed. And then you have this closure of the image of this thing inside of this. Right, and this is where you're kind of taking the closure of the graph. I'll write this in quotes. Closure of the graph of, in this case, I guess, of the map here, which I didn't give a name, but U to MG. Okay, so that's like in essence what's going on, right? Is you're taking this map from U into the moduli space, and you're taking its closure. And then what you're going to get is some projection onto the domain factor will turn out to be an alteration. That's what we're going to see. So in particular, I won't fill in all the details, but this thing has a projection onto Y by virtue of living in the product. And that turns out to be the alteration that we want. So this is the alteration we want. Okay, I'm just saying that. And then you say, well, how did you improve the family? Well, the original family lived over Y like this, X over Y. And we just found this new thing, which maps to Y by some alteration, which is a generically finite proper and dominant morphism. Right, that's what we have now. And then you can, but this thing has a map to, right, there's also a projection onto the other factor. This, right, let me actually do this. Right, it lives in the product, so it has projections onto both factors. In particular, it has another projection onto this thing. Right, and so let's see. Let me not write this yet because this is confusing. So, yeah. So there's a morphism this way, right, onto the other factor. And then the important property that we need to know about this thing is that, you know, the moduli stack didn't necessarily have this property, but this finite cover does. It has a universal family that lives over it. So this sort of universal curve that lives over this thing. And so you can pull back the universal curve to this base instead. And then you get a new curve, like a new family of curves. And in particular, this new family is improved. This is the whole point, because the geometry of the moduli stack of curves has the property that when you take the closure, you incur only nodal singularities in the fibers at worst. Right, so this new family has at worst nodal singularities in the fibers. So that's the big step. That's why you want to use the moduli space at all. It's because you know some stuff about its geometry. Now the problem is we don't know how this new family relates to the old family. I mean, one thing that we know is that we have an alteration right here that goes from this closure onto Y, right? And we can try to pull back along that somehow. Right, like take this alteration and form this fiber product, right? And then you get a new family. We'll take the reduction technically. You have to be careful. You have to make it reduced. Well, let me not call that green. Let me write this in yellow. So this is like the pullback of the old family along the alteration. This thing that we have here. This is the pullback.
But normally when you pull back on the longer modification, the pullback is not enough. You have to kill the torsion or something in that to get what do you call that? The name escapes me now. The strict transform.
Yeah.
Is that what?
Yeah, so actually, so I looked into this because I didn't want to talk about the strict transform because I thought it would be confusing. It turns out that in the varieties case, when you take the strict transform along an alteration, which is projective and like all the stuff that we're like in the case that we're in, all you have to do to form the strict transform is you take the fiber product and then you take its reduced subscheme.
Okay, yeah, because then okay, I see, because you kill the tor. Okay, yeah, okay.
No, it's a great point. So if you try to read the paper, you'll read about the strict transform, and it's kind of like, what the heck is this thing? But it turns out that in the varieties case, it's actually very concrete. You just take the fiber product and then you take the reduced subscheme.
Right.
Yeah, but that's a great point because it confused me for a long time. So it's like totally fair. So pullback of old family over the altered base. Okay. And now the problem is, how are these related, right? Like, is this old family related to the new family at all? Right, so what's the relationship? Like, is there a map between these things? More precisely, is there a morphism between these two things? Because remember, an alteration of if we want an alteration of X, it has to be a morphism onto X. It can't just be a map. Like it has to be everywhere defined. So we now need to check that this actually makes sense. Like, can we sort of justify this? So let me now rename things because the naming is getting out of hand, right? These things are ridiculous. So let's call this now like curly C or something for curve. And then let's just update the base. Let's just start calling this Y now, right? Because we're going to throw out the old base. We're just going to forget about it now. Like, we don't need it anymore, so just get rid of it. And then we have a new family. So let's just update this. Let's just start calling this X now, right? And then this is still Y down here. Right, this is still Y. So what do we have? We have C over Y. And then we have X over Y. And notice I didn't draw anything between C and X. And the reason I don't draw anything so quickly is because I don't actually know that what lives between C and X is a morphism. All I know at this stage is that these two families agree over an open set. These two families are the same over an open set. They're isomorphic over an open set, more precisely, which means that there's some map, but I don't know that it's a morphism yet, that goes from C to X. And so we need to know, to sort of continue, we need to know that beta is a morphism. So we need to argue somehow that beta is already a morphism. And so you might say, like, well, there are other things you could do. You could, like, we learn in algebraic geometry that if you have a not everywhere defined map, you could just, blow up along the indeterminacy locus and make it everywhere defined. You say, yeah, I mean, sure, go ahead and do this. But if you do that, you might ruin the stability of this family. Right? We worked very hard to make this a stable family of curves. So if you now just start blowing up along some non-reduced indeterminacy locus, you could completely ruin that, right? So we don't want to do that necessarily. So we prefer not to disturb C at all and just kind of hope that this is already a morphism. That's the hope. And of course, you can blow up X as much as you want, but that's not going to help you get a morphism back, right? We need the morphism to go from C to X. So we have to be careful. So the way that we try to do this is pretty cool. It uses like a very classic idea. You know, if you have a map that's not a morphism necessarily, you can study its graph. Right, so we study the graph, or the closure of the graph of beta, right, inside of the product of C and X over Y. And in particular, we focus on the projection, which we'll call like PR1, and that goes from the product onto C. And what we want to show is that PR1 is actually we already know it's birational, right? Because it agrees with, you know, it already is an isomorphism on an open set. But what we don't know yet is that it's finite, which means in our case, we need to show that it has finite fibers. The properness is all there because everything inside is proper. So that's not an issue. We need to show that it has finite fibers, and then it's a morphism that's already taken care of to a normal variety. I mean, yeah, in this case, a normal variety is fine. Let me just quickly say, I'm not going to get into the details here.
Sorry, when you say PR1, you really mean PR1 restricted to the closure of the graph, right? That's what you talked about.
Yeah, excuse me. This is not supposed to be from here, right? It's supposed to be from the closure of the graph of beta. Yeah, sorry, living in the product. Excuse me. Yeah, thanks. Yeah. And then I just want to say a few words, but I won't get into any detail about why you can assume this is normal. Okay. Just take the yeah. So what you do is you make the base normal so you make the base of C normal by taking the normalization, and then you can, I think, yeah, something like this. So stable curves over a normal base, like a family of stable curves over a normal base, is actually stable, and base change of a stable family is still stable. So if you base change the base Y by some normalization, you're not going to change the stability of the total family of the total space. So you're allowed to do that. You can take the normalization of the base, pull back along that, make the base normal, and then you'll have something over a normal base. And if it's a stable family over a normal base, then the whole thing will still be stable. Like you won't, sorry, yeah, it will still be stable because you just base changed. And in fact, the total space will be normal. So we can make C normal is the point. So I'll just say like after some base change of Y, after some normalization of Y. Anyway, if people are curious about that, maybe I can talk about that later or something, but you can make C normal, that's the point. And then once you made C normal, you say, well, then most of the hypotheses that we need are sort of here. We want to show that this is a birational finite morphism to a normal variety. The only thing that we don't know is whether this is a finite morphism. That's the crucial thing, which means we need to know that somehow this has finite fibers. That's what we need to check. And then if we can show this, right, so if we can guarantee this.
Which arrow has finite fibers?
This one. So the projection from the graph onto the domain. Yeah. So if we can guarantee this, a classic theorem, right? Zariski's main theorem takes over, and that morphism PR1 is actually an isomorphism. And then that's a big deal because then what you can do is you can now travel sort of backwards, because now this thing has an inverse, and then along the other projection to get to X. And so the composition from C over to X. Oh, that's cool. Yeah, don't worry about it, Andrew. Maybe you've already left, but yeah. So if you have an inverse, you can go from C back to X, right? And then this the composition PR2 composed with PR1 inverse is well, I'll say agrees with beta over, right, the open set where beta is defined. And so beta extends already. Extends to a morphism already. That's what we need to do. We need to show that the fibers of PR1 are actually finite, so that this inverse exists by Zariski-Smith theorem. So this is really where you use the stability of C. And notice so far I haven't said anything about marking the points, because I actually want to show why we won't be able to do this unless we know something about these markings, which I haven't mentioned yet. And then I can say, well, if we have these markings, then we'll be able to proceed. So I'm going to draw a cartoon of the graph of the closure of the graph, you know, inside of the product. Oh, sorry, I don't want to go immediately to the graph. Let me do a cartoon of the, sorry, cartoon of a fiber of the graph inside of a particular fiber of the product, like a particular fiber of this. Yeah, so let me just call this like sub y in some sense. So we're just going to look one fiber at a time, and that suffices, right? Because we need to show the fibers are finite. So we'll just look at one fiber at a time. The argument is general, so it's fine. So the cartoon is that, you know, your C is like the domain. So there are some curves in the domain, right? So there's some pieces in the domain part, and then there are some parts of the fiber X which might break up into irreducible components also. Like it could look like this. So this is like X sub Y, and this is like C sub Y. Right? These are the domain and the codomain parts of the, like, if you were to draw the graph, right, it would kind of look like this. And then the graph lives inside of here. So I'll try to draw the graph somewhat. All right, so I'll say if the fibers aren't finite, then the fibers of PR1, right, fibers of this projection onto PR1 is going to map onto here, remember. So if the fibers aren't finite, then some curve in the graph, in the closure of the graph, like this fiber or whatever, is contracted by PR1. So like the picture to have in mind is like, imagine you have some vertical component, and then when you take the projection, that thing gets smushed to like just a single point, like this. we're trying to rule out this possibility. That's what we're trying to do. We want to show that this type of thing doesn't happen. So I'm going to assume that it does, and then show that that leads to a contradiction. Right? It leads to some problem about the stability of C in some sense. So let's assume, right, by contradiction, some fiber is contracted. That's the only thing that could happen otherwise. And then, yeah. So if some fiber is contracted, I mean, that doesn't really cause an issue as of now, right? Like, that's fine. I mean, like, you're allowed to contract a fiber, and it doesn't cause any contradiction about, you know, the stability of this curve C. But if I know a little bit more, like if I know that there are some points maybe that I marked at the beginning of the argument, say over here, on each of the irreducible components, and I'll start with 3, and I'll try to explain why I really do need 3. Then these have some irreducible components that they map onto. Maybe on this closure of the graph fiber, and now these markings would get mapped to some markings on, right, on this how should I say this, on these well, I'll just say, yeah, if you take their pre-images, they get sent onto these components, or these pre-images are these components. And because these curves down here are stable, or sorry, this curve is stable, we know that
Why do these points become curves?
yeah, so well, I'm trying to think of how I could like what if they didn't, sort of thing. So I don't know if I can answer that right now, to be honest.
You're going to use it?
Yeah, I am going to use it. Yeah, I am going to use this, but I don't know if I can say.
So, I mean, I thought you were going to say if that vertical line gets collapsed, there are other branches passing through that, and then the image of that doesn't look like a curve with normal crossing. No, if you had two things coming together like that, and you collapse, like if you had three things like that, and you collapse the vertical thing to a point, it wouldn't look like a curve with normal crossing. It didn't look like that. You'd have three things crossing at a point, and they'd be squished together somehow.
Well, yeah, that's how I want to use the fact that these are curves, actually, is that when this vertical part gets contracted, right, then in the image, it's going to look like what I'm about to draw.
Okay. Well, that's already a contradiction because you have other curves.
Right, it would look like this.
Yeah.
Right. Oh, I see. I see what you mean. Like you already have this curve, right? That's what you're saying. Like, why do you need?
No, but it could very well be that one component maps onto that whole curve. So you need three probably. One of the reds could be equal to the green. So then you still would have only.
Oh yeah, yeah. My
But
picture.
then,
My picture is deceiving, right? Because it could be that, yeah, like Hans is saying, I guess you could have this. Like maybe this thing actually looks like this, right? In which case this thing is going to get like nicely mapped onto here, right? It's gonna cover it. I'm not going to draw it literally on top of it, but like it could end up just being on top of it, and then I would need.
We can't see what you, okay, now we.
Does that make sense? Like, so thanks, Hans. Yeah, that makes sense, right? What if this thing gets sent onto this thing? Exactly. Like, right? What if this gets mapped isomorphically onto this? Then you would need these two things to help out, or else you wouldn't have enough crossings. Is that okay? So that's one possibility. Then the other thing that can happen is so
Well, you haven't demonstrated why the 3 points are really used.
well, yeah, let me sort of proceed a little bit with this. Let me step away from this thing for a second and keep going sort of in the way that I was going to do it, I think, and then you'll see. So not only would we have to have marked points on each irreducible component, but we would have wanted to have made sure that those markings got sent to markings on each of these irreducible components. So like the markings that are on this one would have to get sent to, let's say that this component gets mapped onto this. Like when I pull this component back, it gets mapped onto this particular component. Then these points have to get sent to markings on this curve is also what we want to arrange. Like we want to know that these markings get sent to markings here. Now, if that happens, then yeah, then the preimage of this is this curve, which has to get sent to, yeah, so either this vertical component has to get sent to a point which is in the set of markings, or it doesn't. Like this is where it doesn't. This is a picture where the vertical component gets sent to a point that is not in the set of markings for this component. Now, if this happens, so if it gets sent outside of the markings, then the picture is like what I drew before, right? It would be like maybe this with these markings, and then these components would go through here, and maybe one of them would get mapped right, maybe one of them would get mapped entirely onto the green component, like this. I guess. But actually, yeah. So maybe one of them does, but then no other one can get mapped to that component. So that has to be proved. Fair enough. But I can't have like both of these components getting mapped to this component, which is what we might be thinking, like, well, if I just map all of these components onto the green component, then there's no issue, right? So like no matter how many points you had, it wouldn't be an issue. But it turns out that if one of these things gets mapped onto here, no other one can get mapped onto here. That has to be proved, I guess. So like this is the worst thing that could happen, is that this thing gets mapped onto here and these then can't. And so this is sort of the worst case, in the case that this gets contracted outside of these points. I don't know if this is believable though. I'm happy to try to address questions if people have questions, because this is kind of the whole point of the talk anyway. So, so there's a claim.
Oh, wait. Let's see. Generically, you're good, and every component has 3 points, and the families agree, right?
Yeah.
Generically, the families agree, right?
Yes.
And then when you form the closure of the graph, these new things appear.
Yeah.
And do they have 3 points?
These things here.
The new things that appear when you take the closure of the graph, do they also have by continuity some 3 points?
Oh,
Yeah, were your points not given by a divisor that cuts?
yeah. They're still there because, yeah, like the way that we would get these points is, yeah, by cutting the variety by some divisor, and then when we take the closure, that will come with it. But I guess, yeah, you have to worry, like maybe when you take the closure, the points don't necessarily come along for the ride, but they do in the open part, but then you have to worry about, like, does it happen in the whole closure? And I think the answer is yes. Like, yes, every fiber, even in the closure, is such that every irreducible component is marked by 3 points. That's true. But I'm trying to think of why, like, what's a good argument for why that has to be true. So at the very least, I can say for sure that yes, when you take the closure of X, it's definitely true that each irreducible component, even the ones that come in by taking the closure, have markings in the fibers. So I can say that at least. It's definitely true.
You're taking the closure inside this moduli space.
Yeah. With the marked points though, right? The moduli space comes with that extra structure, the one that I'm going to use.
And clearly you're taking the closure in there, so all the new things have marked points, and they all have 3 marked points.
Yeah.
Okay, so then no fiber could be crushed. No piece could be crushed. It's got 3 marked points that go to 3 points.
Well, none of you mean no fiber of the graph, like, or no fiber of
Studying morphism, the projection, right?
Yeah, this one. Yeah.
You're studying the projection, but I'm not. The red thing doesn't mean anything to me because it's like you have these dotted lines, and it's no, but you're just closing in the moduli space of marked things.
Mm-hmm. You're
forming the closure, right? And then you project it, right? And the points go to the points. They're separated.
Yeah.
So no, you know, if even 2 points, if you had 2 points on each component that went to 2 different points, that component couldn't be crushed. Because that would identify 2 points. Is it?
But what if the points, what if the part that gets crushed is outside of the other points? Then that,
No, but they get crushed. No, but the points,
like these points, you mean?
don't the points, oh, I see. We don't know where these points are going.
Yeah, like I could take these 3
Two
points.
curves have points, but under this projection map, we don't know where they're going.
Yeah, they might end up crushing to a point that's outside of the other points, right? Like we have markings on both factors, right? But when we take the markings off of the factor onto the component and then crush them, we don't know that they hit the 3 things downstairs. They might miss those.
Well, no, I want to use the fact that the points are kind of marked points. They're in violet. You're closing in the space of things that as marked points.
Mhm. Yeah, but
I don't see how you've used the marked points now. I mean, the way you're talking about.
okay, so
Under this map P1, do the marked points map automatically to marked points just by logic?
not necessarily, no. These marked points on the left don't have to mark, they don't have to map to these marked points necessarily.
Which factor is the moduli space? The horizontal?
Yeah, this is the stuff that we got from the moduli space.
I mean, the universal curve part, I mean?
Yeah, exactly. This is the universal curve thing, right? The thing we got from that part.
So, but what is the argument? If perhaps, can you wrap up the argument kind of? No, what happens now? Okay, you have this picture on the left. I don't understand why do you need these markings there? What you get is that picture should be part of this family of stable curves, of this whatever universal family, but it cannot because it has 3. It's not normal crossings. Is that the argument?
Yeah. So if this is contracted outside of these markings, then the problem is that you'll have 3 intersections, which is
right.
Which violates the stability of C.
Okay, so that's okay. Let's. I don't understand what happens then if the contraction happens inside a mark point.
Yes.
Why is that different?
Yeah, so I'll show what the problem is. So if it happens that the contraction occurs at one of the mark points, right? So suppose it gets contracted onto this one, for example, then you'll have, let's see, something like this. Right, so this one will go there. They'll all go through here. Maybe they overlap. I don't know.
Still bad.
Yeah, but the thing that's, well, yeah, the real issue is that now there's a singularity at a marked point, which is not allowed, right? Like, so like even if you didn't have all of this, right? Like, if this got contracted to a marked point, that would be a problem because then you would have this picture, right? Like one of these curves would be, if even one of them went through the marked point like this, that would be a problem because now you have a marked point where a singularity is. So that's not allowed either.
Yeah, but it's still also the picture would still be on the left. I don't see that the markings on C play any role. If you have these 3 components that project down to 3 different components that intersect in the same thing, it's always not allowed. So it always gets a contradiction, regardless whether it's within a marking or not a marking.
Yeah, but what he's not saying, he hasn't said where these three components come from. Somehow the three components come from the idea of three marked points, and that was not,
Right. Yeah. Right. Exactly. That I'm assuming that argument was correct.
no, that was not explained. How the three of the marked points also is somehow logically giving three components passing through the curve that might be collapsed, giving the contradiction. But where do those three components come from?
Yeah, so that's fair. This is not explained.
Yeah, but as you said, these points come from, there is a divisor that cuts this thing. And so what happens in the closure is, okay, you have this divisor, but this divisor now is no longer normal crossings and it has more components, like this vertical component. But the three red components that you drew horizontally are the ones that do the cutting, that mark the points in. Is that not your original divisor? They are there anyway. It's just the vertical one that is a new one.
Yeah, I guess that's.
Come on, I mean, you have a certain concrete construction. I mean, you have to say where these three things come from. I mean, you're getting. I agree. This gives the contradiction that it doesn't look right downstairs, right?
Yeah.
It has to do with the nature of setting up these marked points.
Right.
Yeah. And I guess, but at the very least, do we see why there need to be three?
Well, I don't see any relationship between marked points and getting new divisors in the closure of the graph.
But just so that I understand, like, suppose that
dotted lines mean. What do those dotted lines mean?
it just means that, like, this is the fiber over this. Like this thing's pre-images this under the second projection.
Okay, but say it in terms of what you've done here. You have a family of curves, and then you form this closure, and the base of the family cross the universal space, right?
Yeah.
Okay, now you go to a point in the closure. Maybe you do the closure downstairs and then look at the universal family over it. Well, okay, relative to this, you have the argument, right? Okay, so
well, like, are we convinced now though that we need three? That's like, suppose that this is true, right? Suppose that I did explain this.
yeah, no, I'm happy then.
Okay, like you can't.
And I have to go now though. Okay.
Okay.
Yeah.
Thanks.
Yeah, but I agree to three is necessary, right?
Definitely.
Because yeah. So because exactly. Yeah, because I mean, I think your picture is a bit misleading in that you project these two, the left-hand side picture. Okay, one coincides with the green curve, but I think they all have to coincide with, they all map onto generically onto this green. The point is that if they all cross this one vertical fiber, then in the projection, they all intersect each other. But in reducible components, these green components should not do that. There should never be three intersections.
Yeah.
So that's why we need three. Yes.
Yeah. So we definitely need three for that reason, because I don't think that this actually can happen though, right? I think that,
No, in fact, I think it always happens. I think it's the opposite way. These things, these red curves that you draw on top, these are the original ones from the morphism. No, it's the vertical one that is that comes from taking the closure. I'm not sure either. Actually, the picture is a little bit vague for me now too.
yeah, I think yeah, like usually the way that a vertical fiber like this comes up is when you take the closure.
Right. Exactly. Yes.
Yeah.
But the other ones are not. They are originally there, so they must map to the green ones downstairs, because there you had the map. I mean, a morphism.
But so when you say they map to the green one, do you mean
Like this one? Yeah, like that. Yeah.
Oh, so but then that would seem to say that they all do this.
I think so. That's what I originally thought. And then then it comes to a contradiction. No, but that cannot be, because then you have 3 green components intersecting at the same point. That's not a stable curve. I thought that what the argument would be, but perhaps I'm misunderstanding it now too.
So it's like so it's like so something that would have to be sort of said is like, why don't these all just end up on top of this one?
Because they're marked different. They come from different markings on the purple one. That's so they. Yeah. Okay. I'm not 100% either sure. Yeah.
Like maybe if this was say 1, 2, and 3.
Yeah.
Then maybe like what if this gets mapped on in such a way so that this is like.
But then the original one would not be a morphism. Then you would. The original one was an isomorphism. But sorry, was birational map, right? So then these 3 points must go to cannot.
Yeah, over the open part, these things. Well,
Yeah.
what I'm worried about is that it could look now that everybody's bringing all this stuff up. It's like what if it looks like this, right? Like, what if you had these 3 points, and then you manage somehow, I don't know, to make it so that this one went here, this one went here, and this one went here. Like all 3 of them, like this one comes down and happens to land perfectly, and maybe this one comes down and happens to land perfectly, and this one comes down and happens to land perfectly, right? That wouldn't be, that mustn't happen, right? Like that has to be
Right. Not right.
has to be
No.
possible.
Yeah.
But, it's not clear why you can't have that, I guess, is fair. That's a fair thing to say. Like, I haven't explained why you can't do that. But that shouldn't be possible. If you believe that,
Yeah.
this is a
No.
nice. No, it's good actually. It's really good though, because otherwise, it's like, you think you understand these things, and then people are like, oh wait. But yeah, so this probably this should not be possible. There should be some conditions that make sure this doesn't happen, and then this type of thing must happen.
Yeah. Right, and then you have a contradiction. Yeah.
And that's how the contradiction happens.
Mm-hmm.
The other thing that could happen, like you said earlier, is like, what if the vertical component gets mapped to one of the markings? Well, then you have a singularity at a marked point, which is not allowed either.
Okay. Yeah. Yeah, but I'm saying I don't see that that's a different. I don't find that a different problem, because it still would have these 3 components. There would be still 3 because now you drew the only one, but the second one would already also, regardless whether it's. I'm saying the left side is already excluding whether this is on an X or not an X. It's always taboo.
If you still had 3 of them, you would still have that picture.
Yeah. The picture is always there, so it doesn't matter if it's on the marker or not. Yeah, I think we should perhaps wrap it up here a little bit, because I mean people had to go, and
sorry.
picking children up and stuff like that, and I kind of have to go too.
Okay. Yeah. So thanks for sticking around if you did, and then and thanks for
but I think it helped. Now I actually, it's good that I've seen this now 3 times, you explaining, and more and more I start understanding what is really going on. So it was helpful for me, very helpful. Yeah,
it's been helpful for me, even just to try to talk about it, because it's definitely a weird step. Like, but you see why you really need these points. And then
Mhm.
I should quickly say though, the reason I brought this up, like in 2 seconds, there
Yeah.
is another way to do this argument and use a different stack.
Yeah, you mentioned the Kontsevich moduli stack. Yeah, but yeah.
If you do this with a different stack, the Kontsevich moduli stack of maps instead of the curves, then this morphism that I'm trying to get is built in.
Ah,
I don't have to do all of this, and that's actually what that's what I think De Jong is trying to do now, is like write this up more carefully. Because this thing about the divisor is kind of annoying. It's like kind of weird, and it's not obvious why you need to do this, and then it turns out like, you don't need to do it, but you still get a finite cover because this is still a stack. You know, it's not like
Yeah.
honestly.
Okay. Right. Yeah.
That's the last thing I'll say is like, don't worry if you don't understand this, because eventually this will probably be written up in a way where you don't need to know this.
Oh, okay. Okay.
Yeah. All right.
Yeah. Thanks a lot, James. Anybody else has questions? Is there anybody left actually? Yeah. No. It's just
Yeah.
GB and Faye are left.
Yeah. Thanks for sticking around.
So we will definitely post this then, and then everybody can look, because I'm sure Andrew would also want to hear the end of the talk.
Yeah, and I guess I'll have my own battles with Dennis.
Yeah.
Good though, because I remember that was the first thing he said to me. It was like, "Why the 3 points?" You know.
Yeah, I know. But at least he was convinced that 3 was necessary now.
Yeah, I wanted to get that at least.